Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be going over how to use the electronegativities to classify bonds. So let's get into this. So what we're asked to do here in this video, or what I'm going to go over, is a particular problem where you're asked to classify a bond as either nonpolar, covalent, or polar covalent, or ionic. And I'm going to show you how to do that using the electronegativities. Now, a lot of times you can kind of just eyeball it and see like where they are on the periodic table. If they're pretty far apart on the periodic table, like if you got a metal and a non-metal, that's pretty much going to be an ionic bond, right? So, but if you got a metal, if you got two non-metals, you can kind of figure out whether it's going to be non-polar covalent or polar covalent by how far apart they are. But if you really want to make sure, then you would look at the electronegativity differences. Now, I want to specify we're not going to be looking at the electronegativities per se. We're not going to look at directly those, which we are going to be using, but we're not looking at the electronegativities themselves. We're looking at the difference between the electronegativities of the two bonded atoms. That's what we're looking at. That's going to tell us if it's going to be ionic, polar covalent, or non-polar covalent, that difference in the electronegativities between the atoms. So if you look here, I have written down here that this triangle means difference. So the difference in the electronegativity, if that difference in the electronegativity between the two atoms is less than 0.4, then we would consider that a non-polar covalent bond. Now, some textbooks may say less than 0.5. So, go with your textbook or go with whatever your professor or your teacher says. But the idea is that below a certain threshold, the difference in electronegativity would indicate a nonpolar covalent bond. If your difference in the electronegativity between the two atoms is somewhere between zero point 0.4 or 1.7, if it's in this range here, then it would be polar covalent. Again, depending on your textbook, I've seen textbooks say 2 here. So if it was between 0.5 and 2, if the difference in electronegativity was in that range of 0.5 to 2, then it would be a polar covalent bond. So again, go with whatever your professor, your teacher, or your textbook says. Here, if you have an electronegativity difference between your two atoms that is greater than 1.7, then we would consider that ionic. Again, if some textbooks are going to say if it's above 2.0, then it's ionic. Again, go with whatever your teacher, your professor, your textbook says. But for this video, we're going to use these ranges here. So let's look at our set of atoms that are bonded. So A says oxygen is bonded to hydrogen. So is that going to be a non-polar covalent, polar covalent, or ionic? Well, we can see that's two non-metallic atoms. So chances are it's not going to be ionic, right? So this is going to be some sort of covalent bond. And then we can see that, hydrogen and oxygen are pretty far apart, so probably a polar covalent bond. So let's look at our electronegativities. So you're going to need an electronegativity chart. That would be like a periodic table with the electronegativity numbers written on it. So if you look at that chart, you'll find that oxygen's electronegativity is 3.4. So let me use a different color here. So oxygen, we're saying that was 3.44. So I'll write it down here, 3.44 for its electronegativity, and 2.20, I believe, for hydrogen, 2.20. And so that's going to give us an electronegativity difference of 1.24. So 1.24. So because this is an electronegativity difference between these two is 1.24, then we're within this range here. So that would be polar covalent. So I'll put PC, or I'll just write it out. Polar covalent. Okay, now, oops, there goes my marker. All right, so for B, we're looking at carbon bonded to sulfur. So again, we have two nonmetals, so we would expect this to be covalent, not ionic. Also, carbon and sulfur are relatively close to each other on the periodic table, so we might think that this might be maybe non-polar covalent, but we'll see. We'll look at the electronegativity differences. So for carbon, we look at our electronegativity. One thing I want to also point out. So this is a polar covalent bond. So we need to decide which atom is a partial negative and which atom is a partial positive. So when you're determining what atom, what side of the bond or what atom gets the partial negative or partial positive, always remember what electronegativity means. Electronegativity is the desire, or if I can put it in anthropological terms, like desire or the wanting, or it's the force by which it's going to attract electrons in the bond. And in this case, oxygen has a much higher electronegativity, so it's going to attract those electrons much more strongly. So the electron density is going to be more on the oxygen side. Electrons are going to spend more of their time, more of the probability is going to be around the oxygen. So then we would put or assign a partial negative to the oxygen. So the oxygen would have a partial negative. So we'll put a partial negative. That's a delta negative, like lowercase delta. So delta negative for the oxygen, and then we would have a partial positive or delta positive for the hydrogen. Okay. Okay, back to carbon and sulfur. So let's look at the electronegativity differences for carbon and sulfur. Gotta fix my B there. Okay, so for carbon, it's 2.55. So we'll put 2.55 there. And then for sulfur, where's sulfur? 2.58. 2.58. And we're getting an electronegativity difference. That's pretty small, actually. 2.55, 2.58. That's 0.03. So that's much less than 0.4. So we would label this as non-polar covalent. Okay, so I'm going to write down non-polar covalent. Okay, good. Okay, now let's look at C. We have lithium and chlorine. So lithium is a metal, chlorine is a non-metal. So we would expect this to be ionic because we get ionic bonds from metals and non-metals because of a complete transfer of electrons. So let's go ahead and look at this and see if we're right. So the electronegativity, if it's ionic, the electronegativity difference should be greater than 1.7. Okay, so lithium, where's lithium? Lithium has an electronegativity of 0.98. So we'll put 0.98 there. And chlorine, that has a pretty high electronegativity. Its electronegativity is 3.16. 3.16. So the electronegativity difference, or difference in electronegativity, is going to be equal to 2.18. And so we see it is indeed above the 1.7. So therefore it is indeed ionic. And hydrogen bonded to fluorine. So again, we have a nonmetal and a nonmetal, so we would predict this to be covalent. These are, again, relatively far apart. Fluorine is the most electronegative element on the table, so my guess would be that the difference in here is going to be within this range here, probably closer to 1.7. But let's take a look. So hydrogen is the same. We have an electronegativity of 2.20. Fluorine has an electronegativity is 3.98. So 3.98. And so that's going to give us, let's see, it's going to be the electronegativity is going to be equal to 1.78, I believe. 1.78. Now, notice that it is above 1.7, so we would expect it to be ionic, but in this case, we have two nonmetals here, so we're going to label this as polar covalent because we get ionic bonds not from two nonmetals, but from two a metal and a nonmetal. So we would label this as not nonpolar, polar covalent, polar covalent. Polar covalent. And so again, we want to label these as either partial positive, partial negative, because it is a polar covalent bond. And so which side would have the positive, partial positive, which side would have the partial negative? So since, again, the partial negative side goes to the more electronegative atom, because again, the electronegativity is what draws the electrons in the bond towards it. So the electrons are going to spend more time over by the more electronegative atom. And so we would label this fluorine as a partial negative. And then therefore, since the electrons are kind of being pulled this way, this is going to give the hydrogen a partial positive side. So maybe this is an argument, since the electronegativity difference is 1.78, this might be an argument as to why some textbooks or professors would say that if it's greater than 2.0, then it's ionic, right? And then the range here would be 0.5 to 2 would be polar covalent. So that seems to fit better with this, but it depends. So I hope, sorry about that. I hope this video helped you out. If this was helpful in any way, if you like this video, then please like the video, hit that like button. Also, make sure you share this video with your friends and subscribe to my channel. Hit that notification bell. When you do, make sure you click all, and that way you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you want me to go over for you, or if you have a topic you want me to cover, I would love to do that. Thanks for joining me, and have a great day.